Great. So thank you very much for the invitation to speak today. So I'll be talking more about observations and talking about a little bit of what are the observational constraints, what's the information that we have to date about how protoplanetary disks evolve into planetary systems, which is a fundamental question in astronomy. And I labeled this talk a multi-wavelength perspective just because I'll be looking at protoplanetary disks emit at many different wavelengths and what information can we get at different wavelengths. All right, so first, a quick overview on protoplanetary disks. So these are complex systems, dynamic environments. The disks are made up of dust and gas, 99% gas, and that's represented here in the brownish orange shaded area. And if we start on the left and work our way in, you see some of the processes that are happening here. We have dust settling, dust settles to the midplane. We have turbulent transport. We don't know exactly how that happens. But the idea is that dust grains in the upper atmosphere, the smaller grains, they settle to the disk midplane, they collide, they stick, they grow, they become bigger, eventually somehow getting to planetesimals and forming planets. So we should have a more dense, more dust in the midplane of the disk. And then there's also snow lines as you get closer. As the temperature gets colder, depending on the species that you're looking at, but that can also facilitate the coagulation of grains and dust growth. Now, if you look at the right end of the disk, you'll see more about the chemistry that happens in these protoplanetary disks. I don't have a lot of time so I won't be talking about the chemistry, but basically as we get deeper and further away deeper into the disk and further away from the star, the disk gets colder. Whereas here, very close to the star, the temperature is about 1500. And this is what's called the inner dust rim of the disk. So there's an inner dust rim and an inner gas rim. That's over here in green, close to the star. And then here in red is the inner dust rim. That's where dust sublimates. But gas can still flow inward onto the star and accrete onto the star. And I'll talk a little bit more about this in more detail later. All right, so just keep in mind throughout the presentation that disks are not static. Whenever we get observations, we're just taking a snapshot of what's happening in a particular disk at a particular time. But there's a lot of variability in these young systems. The radial accretion changes, the stellar luminosity changes. So just keep that in the back of your mind. And, as I said earlier, protoplanetary disks emit radiation at multiple wavelengths. This is both in gas line emission and dust continuum. So starting here on the left, so the star itself emits at all wavelengths. It's strongest at the shortest wavelengths. And the accretion process onto the star, so we think accretion happens onto these young pre-main sequence stars, particularly the lower mass ones, so 2 solar masses and less, via magnetospheric accretion. And that emits mainly in the ultraviolet. And then as we get further away, we're looking at the gas in the closest to the star that emits in the near infrared. The inner edge of the dust disk, the dust inner rim, that also emits in the near infrared. And then as we get further out in the disk, we start to see emission in the mid infrared, particularly from the disk atmosphere within tens of AU from the star. And then in the outer disk and in the midplane of the disk, we get we can get submillimeter and millimeter radiation as we're getting to the disk is getting more optically thin as we get further out and further out in the disk. All right, so basically we can see protoplanetary disks emit from the UV all the way out to the millimeter wavelengths. So I'll be trying to answer 3 questions, of course, not completely, but attempting to give some information on each of these. So I'll be talking about when do planets form? So at what time in the evolution of a young star do we think planets are forming? I'll show you why we think planets may have already formed previous to what we call the protoplanetary disk stage. And then I'll talk about where do planets form. So we heard a little bit in Sean's talk about how their planets can pile up at the innermost radius of the disk. So I'll be talking a little bit about, could it be migration? could it be in situ formation? And are there ways to test for that in protoplanetary disks? And then I'll conclude with some prospects for future work on protoplanetary disks, mainly focusing on multi-wavelength variability, looking at accretion in these young systems. All right, so the first question, when do planets form? So here I'll be focusing on dust settling and disk dust masses. So two things that we can measure. So the measurements that we have so far of dust settling to the disk midplane and dust masses suggest that planets start to form very early in the disk's lifetime, if not even earlier than the protoplanetary disk stage when the disk is still embedded. So young disks show significant signs of dust settling, which is an early indicator of planet formation. As I said earlier, one of the first steps of planet formation is that grains settle to the disk midplane, and there we have a significant population of dust grains, which allows dust grain growth and therefore planet formation. All right, so here is a schematic quickly overviewing how we think dust settling occurs. So dust settling is when we have small ISM-sized grains in the disk atmosphere that stick together, grow, and they settle to the disk midplane, where they form larger and larger grains. And this is a complicated process that there's still a lot of research on. So this is an oversimplification, but we go from small dust grains to planets somehow. And we think that planet formation happens in the midplane where dust grains are concentrated. And we do see evidence of settling in observations. So here we have resolved images, and it's hard to get resolved imaging for a lot of disks, but for the few that we can get resolved imaging for the biggest and brightest disks, we do see very clear evidence of dust settling. So the top is a disk which is at an intermediate inclination, and at the bottom is an edge-on disk. And in the top, the red is near-infrared emission, which is tracing light, which is scattering off of small dust grains in the surface layer of the disk. And so that's the reddish, and then the purplish here is tracing the sub-millimeter radiation, thermal emission, and that's coming from larger millimeter size grains. So you can kind of see in this, the contrast isn't great, but that these small dust grains are coming from a very flared surface, whereas the larger dust grains are coming from a flatter part of the disk in the disk midplane. And you can see that more clearly in the bottom figure, where again, the red is tracing the small dust grains, that's near-infrared imaging from scattered light, and the contours are tracing here the millimeter emission. So that's tracing the larger grains. So here it's much clearer to see that the larger grains are concentrated towards the midplane of the protoplanetary disk, whereas the smaller dust grains are distributed in the upper atmosphere. And the protoplanetary disk itself is actually the dark lane in both of these images. Yes, and then here we're just focusing on the near-infrared and the millimeter, but if we had different wavelengths, we would be able to fill that in. All right, so, and then it's even easier to see the effect of evidence of dust settling in the edge-on disks, but it's even harder to image these because first you have to, there's a fewer, you're less likely to get a disk that's edge-on versus a disk that's not edge-on statistically, and then you have to get one that's big enough and bright enough in order to get these kinds of beautiful images. So it is hard to do this for many objects. This has been done for about a dozen or so objects. It's much easier to collect spectral energy distributions of protoplanetary disks for much larger samples. So we have SEDs like this, plots of lambda versus lambda for hundreds of protoplanetary disks. And here, the lines correspond to simulations of disks that have different amounts of settling of dust, where this arrow is pointing it in the direction where dust settling is increasing. So this lower line here has the highest amount of dust grains settled to the disk midplane, and then the uppermost line here has the most flared disk. So we can see evidence of dust settling by looking at the spectral energy distribution, particularly in the mid-infrared to the far-infrared wavelengths. So in cases where we don't have high resolution images, we can use the spectral energy distribution. Here in the next slide, I'll show you some modeling that we've done with graduate students in my research group have done, modeling the spectral energy distribution. So here, all the points and lines, and the black lines here are data. And then the blue lines are model fits using an irradiated accretion disk code. And on the left is just an example of fitting one disk. But in this study, my former graduate student, Annalisa Rillinger, she compiled the SEDs for 340 disks in 11 star forming regions with ages ranging from 1 to 10 million years old, and modeled measured how much settling is in, how much are the dust grains settled in these disks. And in our models, I'm not going to go into the details of how we quantify the dust settling, but basically each of these histograms corresponds to different regions, and each of these broken red lines corresponds to a dust depletion factor of about 1,000. And you can see that for some of the regions, they're right at a dust depletion factor of 1,000, but for some of them, they're even higher than that. That's what the black histograms correspond to the measured amounts of dust settling in these disks. So we find that dust is depleted by factors of thousands in the disk atmosphere, and already this is for young systems, again ranging from 1 to 10 million years old. So this is indicating to us, when we look at the observations, that dust settling is well underway to high degrees by the protoplanetary disk stage. And since this is a precursor to planet formation, this is telling us that the conditions for planet formation are there. And it's even possible that planets form at an even earlier stage than protoplanetary disks. Sean showed in his talk the image of the ALMA image of HL Tau, which is a very young disk that's still embedded, and it has those gaps, which some people think are due to planets that are forming in the disk. So combined with ALMA imaging of very young systems like HL Tau that have some indicators of planet formation, and then these studies of hundreds of disks looking at dust settling, the picture that we're getting is that planet formation happens early in the protoplanetary disk lifetime. All right, so then another way, so we talked about dust settling, another way to get insight into planet formation and the conditions, are the conditions right for planets to form out of protoplanetary disks, is to measure what are the masses, particularly the dust masses of protoplanetary disks, because dust is easier to measure than gas. And then we can compare that to what are the masses of exoplanetary systems. So count up how many planets you have in exoplanet systems and what masses are necessary in the protoplanetary disk stage to form them. And we can compare the two. Now, it seems straightforward, but it's actually very difficult to do this. As I said earlier, 99% of the disk mass is in gas, particularly cold H2 gas, which we can't observe. So we only have indirect tracers of what is the total mass of dust, of the total disk mass. And as I said, we focus mostly on the dust mass because dust masses are easier to measure than gas masses. So here are some examples of, here's one example of why it's so difficult to pin down masses of protoplanetary disks. This is TW Hydra, the closest protoplanetary disk, the best studied protoplanetary disk. An overview of the observations that have been gathered for TW Hydra on the left, but what I want to focus on is the plot on the right, which are disk masses that have been measured for TW Hydra, one disk, with all of these different observations. On the bottom x-axis, you see the disk mass. On the y-axis, on the bottom part, which is shaded blue, you see disk masses that are derived from the dust continuum, looking at the SED. And on the top, what's color-coded orange, those are measurements from molecular lines. So what you see is that, and then usually when we get the dust masses, we multiply that by 100, the gas to dust ratio, in order to get to the total disk mass. But basically the point here is that you can see there's a very large spread in the measured disk masses for even the best studied protoplanetary disk to date. And there are many different reasons for that, probably. So gas can freeze out onto grains. There are assumptions that have to be made on chemical abundances when you're taking these measurements. There can also be particularly, so that's for the gas. And then when we look at the dust, different people assume different temperatures and opacities when they're measuring the dust masses. So it's very complicated to get the masses of protoplanetary disks. But still, it's still very important to at least try and to see what we get. And many have. One approach as I've mentioned a couple times, is to focus on the dust masses and to get dust masses for large samples of protoplanetary disks and then compare to exoplanet system masses. And there's a lot of work on this, so I'm just highlighting a couple of teams. And here, what is being shown here is the comparison of so in yellow, where are the masses that are extrapolated if you look at the Kepler planets, and in green, radial velocity planets, and then in red, what are the dust masses that are seen for ALMA, disks that are observed with ALMA. And what people find is that the mass in solids, the dust masses in exoplanetary systems is similar to what is seen in disks. And that would imply a 100% efficiency of planet formation, which seems very high. And one thing that can be considered to help try to alleviate this tension, that all of the dust, all the mass in protoplanetary disks has to be converted to planets in order to reproduce the exoplanet statistics that we see, is to consider that there are uncertainties in measuring dust masses, and that maybe the masses of protoplanetary disks that are extrapolated, at least from dust masses, should be higher than what's been reported in the previous, what I showed you. So here's just an example of some dust masses that have been measured for protoplanetary disks. Most of these observations are measured just using one wavelength, because that's what's readily available, and it's one wavelength usually from ALMA surveys, surveys with ALMA. And here you see a list of the different average masses that people get for different star-forming regions. But we have to take into account that if we just use one wavelength to extrapolate the disk mass, the dust mass, this dust mass, that there are some uncertainties on the disk temperature and opacities, and that just using one wavelength can lead to an underestimate of the disk mass. So I told you earlier about the study that was led by my graduate student, Annalisa Rillinger, who looked at dust settling. Well, we also measured the dust masses using broadband SEDs. And on the left are the dust masses here that we measured using the 400 disks in the sample. The red dotted line corresponds to 8 Earth masses, which is just the median to guide the eye here. And then in this right figure here, what we're doing is we're comparing the masses that we derived using the broadband SED, so using multiple wavelengths. So the X is the dust mass from our study using multi-wavelength SED modeling, and the Y-axis is the literature dust masses that were obtained using just 1 millimeter point. We find that the SED-derived masses are about 2 to 5 times higher. And so overall, they're 2 to 5 times higher. And then as we get to even the higher masses, the higher mass disks, the offset is even greater. So this can help alleviate the need to have a planet formation efficiency factor of 100%. It could still point to the bulk of planet formation happening earlier as well. So why is it that our SED-derived masses are higher? So that's because, as I mentioned before, masses derived from just using 1 millimeter point depend on the assumption that the disk is optically thin at that particular wavelength. But what more recent studies are finding with ALMA is that disks are actually optically thick up to some sub-millimeter wavelengths, which therefore means that you can't assume that the disk is optically thin and then use that measurement to extrapolate the entire dust disk mass. And in our model, we don't assume that the disk is optically thin in the millimeter wavelengths. So here is an example just showing that so this particular region is the Lupus star-forming region, and the broken line is an optical depth of 1. The different colors correspond to different disk size, so I'm not talking about that, so don't focus on that. But what this is showing is that some disks are actually optically thick at 1.3 millimeters, which is a wavelength which is commonly used to derive dust disk masses. And so we calculate the optical depth along the line of sight as a function of radius at 1.3 millimeters using our model in order to make this plot. There's still some caveats that we have to consider. So the dust opacity, different people use different dust opacities. We also have to keep in mind that we're just measuring millimeter size grains, and smaller dust could be locked into larger dust grains that we don't have access to. So the point is that disk masses measured from dust masses could and should be even higher than have already been reported in the literature, using just 1 millimeter, using just one millimeter wavelength. So this helps alleviate the tension that we need all of the protoplanetary disk mass to turn into planets. All right, and then the next question is, where do planets form? So here, focusing on the innermost part of the disk, the closest, so looking closest to the star, and here accretion plays an important role in setting the innermost radius of the disk. So here, here I'm focusing in now on the innermost part of the protoplanetary disk, where we're zooming in on a few stellar radii from the star, so about 5 to 10 stellar radii from the star. So here we have the inner rim of the dust disk, and that's where the temperature is very hot and the dust sublimates, but within that, gas can still travel inwards towards the star. Now, these young stars have strong magnetic fields of 1 to 2 kilogauss. So the magnetic field lines actually truncate the innermost gas disk, and ionized gas is funneled onto the star via the magnetic field lines, forming a hot accretion shock on the stellar surface. So what I'll be talking about for the next couple minutes is 2 important radii in the innermost disk, which is the innermost rim of the dust disk, and then the innermost rim of the gas disk. So there are 2 inner radii in the disk. So most people think of the innermost radius of the disk to be where the gas is channeled onto the star, but we'll see the importance of distinguishing between where the gas and the dust terminate in the innermost disk. So if we compare the distance of exoplanets from their host stars to the inner disk radius, we see that there are a lot of short period super Earths and sub-Neptunes, and the periods at which they're detected at are consistent with where you would expect the innermost gas disk to be truncated. So on the left here is the occurrence of sub-Neptunes orbiting FGK stars and early M dwarfs, and there's a peak at about 10 days. And 10 days corresponds to the radius that we would expect for the innermost gas disk where it's truncated. So as Sean mentioned, planets can form further out in the disk and migrate inwards. Another possibility is that planets form in situ in the innermost disk. And one thing that we can try to test for is, it's hard observationally to test for migration because you see the end result of it. One thing we could try to test for is if it's possible to have in situ planet formation in the innermost disk. So there has been some recent work showing that there should be a pressure bump that is generated at the innermost gas edge of the disk, and also at the dust rim of the disk. And if these 2 overlap, that there should be enough of a pressure bump formed there that dust grains can become trapped, and that would facilitate dust grain growth, and then possibly the formation of something like super Earths very close to the star. So for, as you saw in the previous schematic that I showed, we usually think that the innermost gas rim is separate from the innermost dust rim, but we can observationally try to look and see if they overlap in some cases. And that's active work that's happening in my research group. But first, I just wanted to show you some observations that were taken of TW Hydra using the bracket gamma line, which identified the innermost gas truncation radius of the disk of TW Hydra and isolated it from the more distant dust sublimation radius of TW Hydra. So it is possible to use spectral interferometric observations to do this, but again, it's just for the closest stars like TW Hydra. So what we're doing in my research group, and this is an ongoing project, is we're trying to measure the innermost gas disk truncation radius, which we call RMAG, so magnetospheric radius, and measure observationally the innermost dust truncation radius, which we call R dust. And we can measure our MAG, the innermost gas truncation radius, by modeling the H-alpha line. So the H-alpha optical emission line is thought to come from this accretion flow, and our accretion models incorporate the geometry of the system, and they allow us to extrapolate and measure what is our MAG, the innermost radius of the gas disk. And then we can get the innermost radius of the dust disk by using SED modeling of the near-infrared emission, because this is where most of the emission from the inner rim comes from. And this is work which is being led by my graduate student, Kaylee Pittman. And this is work that is ongoing. And we're planning, and she's still working on this, so that work is still in prep. And then 1 minute to just quickly talk about future work that can be done, particularly looking at accretion variability in these young systems. So there was a program, HST Director's Discretionary Program called Ulysses, which allotted 1,000 orbits to study young stars in the UV. Half of those orbits were dedicated towards T-Tauri stars, which are the pre-main sequence stars that I've been talking about today. And our group within the T-Tauri star community, we've banded together and formed a group called Odysseus to help us work collaboratively to best utilize the HST data. And some of our goals are there. And here are just some of the first results papers that have come out from Odysseus, the data collection completed from the HST Ulysses survey in early 2023. So this year we've been going through the data, and we expect many more papers to come out in the next couple of years. But I just wanted to quickly highlight all the different kinds of, this is a multi-wavelength effort. We see here the HST data in the lower right panel that were obtained, but we also obtained multi-wavelength light curves, roughly in the optical B through I. We obtained high resolution optical spectra, and also we obtained medium resolution near infrared and optical spectra. So really, a large effort in the T-Tauri star community to try to best utilize this data from HST. And this, like I said, this survey is ongoing, and we're in the process right now of going through our data and publishing our results. So stay tuned in the near future to be hearing more about accretion variability in these young systems, and it's relevant to what I discussed about the innermost dust rim of the disk and where it's located, because part of what sets the location of that innermost dust rim is the luminosity from the star and the accretion onto the stellar surface. And accretion is variable, so that inner dust rim can change over time. All right, so I'll just leave my slide up here to summarize, and I'm happy to take any questions that you have.
Thank you, Catherine. So